So I am going to be discussing the extra credit problems on the chapter on magnetism. The first question is dealing with a bubble chamber, and it's basically showing paths of some particles in a bubble chamber. There's two spirals. One is kind of going off to the right, one's going to the left, and it's asking what I can conclude about the signs, the charges of these particles. And we're assuming that the magnetic field is perpendicular to the plane of the photograph and pointing into the paper. And which of the two particles, the right one or the left one, has more initial momentum? How do I know? And why did the path spiral inward? So we're assuming the magnetic field is perpendicular to the photograph. And so knowing this, I can tell that the sign of the particle to the right is positive, because if the magnetic field is going into the paper, and we know that a particle of a q charge with a velocity traveling through a magnetic field will experience a force at a right angle to its motion. So in this case, if we're knowing the magnetic field is going in, this particle is going off to the right, V cross B will exert a force that makes a particle make a counterclockwise direction. So knowing that, I know that the particle on the right is positive because it is traveling in a counterclockwise direction. And an electron or a negative charge is going to be the exact opposite. It's going to go in a clockwise direction, and that's what the particle on the left is doing. So I know the right particle is positive, the left particle is negative. And as far as momentum and speed, you can use measurements using Lorenz's equation, which is the force of B equals Q times V cross B, and also R equals mV over QV. And you can solve for V, and then from there solve for momentum by using the, omega equals QB over M. But we can tell by looking at it that the one on the right has more initial momentum because it has a larger spiral. The radius is larger, so we know that it's got more initial momentum. And as far as why the paths spiral inward, this is because of the energy loss of the particle. It causes it to go ahead and turn inward as that's occurring. And so on to the next question. Number 2, a charged particle is fired into a cubical region of space where there is a uniform magnetic field, and outside the region there is no magnetic field. Is it possible that the particle will remain inside the cubical region? Why or why not? And I said that it depends on how the charge is moving. If the charge is moving parallel, then there is going to be no force and the particle will just go straight. And this is from the equation F equals Q V cross B times V cross B. And then knowing that the magnitude of Q V cross B equals QV sine of theta. So if a particle is moving parallel, that's a theta of 180 degrees. The sine of 180 is 0, so that's just going to give you 0 force on there, and it will just continue to go. If the charge is not parallel to the magnetic force, then the force exerted on it will cause a circular motion on the particle, but it's only going to stay in the cube depending on the diameter of the radius. I'm sorry, the diameter of the particle. So if the diameter is smaller, it's greater than the length of the cube, then the particle is going to leave the cube. If the particle diameter is smaller than the length of the cube, then it will stay in the cube and and continue on a circular path. Question number 3 is, if a particle moves through a region of space with constant velocity, magnitude, and direction, the external magnetic field is 0, can we conclude that the external electric field in the region is also 0? So in this case, if a particle moves with constant velocity and there's no external magnetic field, then the external electric field in the region must also be 0. And this is because an electric field always exerts a force on a charged particle. And so if this was true, then the magnitude and direction and the velocity, the magnitude and direction of velocity and the particle's velocity cannot be constant unless there is not an external electric field. I'm getting tongue-tied here. All right, on to question 4, dealing with the spectrometer. So we're given the B and some ways to figure out masses, and also the E in this case. And so it's asking how far apart the lines are from these singly charged ions and what would happen if the ions were doubly charged. So you can find the radius using the equation r equals mv over qv, and we have everything. We can figure out the mass by multiplying 12 times 12, 13, and 14 times 1.6 times 10 to the negative 27th kgs. We can find the q as well and solve for v or solve for r. And by doing that, I did find out the radii were 5.01, 5.44, and 5.84 times all times 10 to the negative 12th meters. So the spacing between the lines is about 4.0 times 10 to the 12th meters. So that's about how far apart they are. And then knowing that, you can solve for velocity by using the equation v equals b over e. And so I got a velocity of 2.74 times 10 to the negative fifth meters per second. And actually I did need that to find the radius. I kind of went out of order there. So if you were to doubly charge the ions, it would increase the denominator by 2 times, which would decrease the radius by a factor of 2. So if the ions were doubly charged, it means that that distance would be decreased by a factor of 2. On to question number 5, which is a charged particle is moving in a circle under the influence of a uniform magnetic field. If an electric field that points in the same direction as the magnetic field is turned on, describe the path that the charged particle would take. So if both a uniform magnetic field and an electric field is pointing in the same direction as B, then the charged particle will move like a helix, and this is because the magnetic field makes it want to move in a circular motion, while the electric field wants to make it go in a straight line. So that's going to give it a helical shape to it. Question number 6 is a doubly charged helium atom whose mass is 6.6 times 10 to the negative 27th kg is accelerated by a voltage of 2100 volts. What will the radius of the curvature be if it moves in a plane perpendicular to a uniform 0.340 Tesla field? And what is its period of revolution? So for this, I did write out the equations. The force of the magnetic field equals mass times acceleration. I got QV, B equals mv squared over r. And then solving for r equals mv over qb. And then also knowing that 1/2 mv squared equals q times delta v. And solving for the v in that, v equals the square root of 2q delta v over m. So we've got mass, we've got the volts. We can simplify that equation to being 1 over b times the square root of 2m delta v over q. And that will give us our hold on a second, and that will give us our radius, which is 2.67 times 10 to the negative 2 meters is the radius. And then once we have that, we can figure out the period using the equation v equals q times b times r divided by m. And that gives us a velocity of 4.51 times 10 to the 5th meters per second. Knowing that, you can use the equation t equals 2 pi r over v. And that gives us our period, which is 3.72 times 10 to the negative 7 seconds. So on to question number 7, which is dealing with a long straight wire carrying a current out of the page towards us. And this one, I do have the last slides that actually have my answers written down. It's probably going to be easier to see this one, but I use the right-hand rule for this. So if I know that at I, the current is coming out, my thumb is pointing out towards me then, which makes of my right hand, which makes my fingers curve to the right. Curve to the left, make them curve in a counterclockwise direction. So up at point C, at that point it's straight above, so the force of B on C is going to be to the left. And so you kind of just envision this counterclockwise direction, circular motion. At E, it's kind of going up, pointing towards like 3 o'clock, I would say, or actually pointing straight at D. That's the force of B on E, is pointing upwards towards D. And then at D, the force of B on D is straight up. So yeah, using that counterclockwise direction, that's how you can see which direction those forces are going. And then for question 8, we're dealing with a circular coil laying on the ground with the magnetic field pointing northward and at a 56.0 degree line below the Earth. And we have a current given to us, so it's asking us to determine the torque on the coil and which edge of the coil rises up. So for this, I use the torque equation, which is torque equals mu times B times the sine of theta. And for mu, that equation is I times A times N, number of loops. For theta, I ended up using 34 degrees, and I got that just because the line, it's 56 degrees below a line pointing due north. So I'm taking 56 minus 90 to get 34 degrees. So to find mu, I did 7.20 amps times pi times 0.08 meters squared times 9 loops, and that gave me a mu of 1.30, which I multiplied by 5.50 times 10 to the negative fifth Tesla times the sine of 30. That gave me 4.01 times 10 to the negative fifth Newton meters for the torque, for the magnitude. And then as far as what direction it's pulling or going to pull that coil up, if the current loop is lying flat on the ground and it's going in a clockwise direction, so I drew two circles, basically like a cross section of this current, and looking down on it. Tootsie, stop. Sorry, my dog is getting fussy. Two circles, both parallel to each other. I have an X coming drawn in the circle to the left and a dot in the circle to the right. So the current is basically going into the page and coming out towards me, which means that the mu, which always wants to be perpendicular to that plane, in this case is going to be pointing downward. And it's also using the right-hand rule to know that. And so knowing that mu is pointing downward and that torque it's basically mu cross B, it means that the left edge or the west edge of that coil is what is going to rise up. And that is all. Thank you very much for listening.